Hello, everybody, and welcome to this last chapter of our course entitled Applications. This is where we're going to see calculus in action, solving problems in real life. So, part one, I would like to discuss the theory of interest. And for that, I will start with the most basic type of interest, something called simple interest. There are actually three types of interest. This one, simple interest. The actual object of this video, which is more compound interest, something important that you will use in life, and something that is actually calculus oriented, which is the continuous interest, which will be at the end of this first video on application. So simple interest. I need a few variables to get started on this. So let A, big A, stand for amount. Okay? Amount is what you have, so the money that you have in the end. Genre, you put $1,000 in the bank and you leave it in the bank for like, I don't know what, 3 years. A is what you get after 3 years when you collect interest. P is the first letter of the word principal. The principal is what we call the money at the beginning. The money that you invest at the very beginning. So at the beginning and at the end. You invest money at an annual interest rate. R for rate. Annual interest rate. You leave the money in the bank for a certain amount of time. T, always in years. Always. T is always measured in terms of years. So if you leave it in the bank for 6 months, then you leave it in the bank for half a year. So T would be 1/2, sort of thing. And finally, big I is the interest earned. Is the interest earned over the period. Over the period. Okay? So this is kind of the basic vocabulary. Let us take a look at what I is. What is the interest that you earn? So we calculate this from a very, I would say, intuitive perspective. The interest depends on three things. It depends on how much you invested in the beginning. Obviously, the more you invest, the more interest you will gather. It also depends if you get a high rate or a low rate. It also depends how long you're going to leave it in the bank. So the way this is calculated is simply P times R times T. This is how interest is calculated so that the amount that you get at the very end is equal to what you invested at the beginning plus the interest that you have earned. Yes? So that A is P plus, and the interest that you have earned is P R T, out of which you can factor AP, and you're going to get, 1 plus RT. That is the formula that actually regulates the simple interest calculations. Now, this is interesting more or less from a theoretical point of view simply because nobody, no bank, no financial institution uses very, very much simple interest. It's still done in some places, but what we have in our lives, in our daily lives, is more like compound interest. So I developed this little formula because it's also the basic part of compound interest. So let us actually leave simple interest and go to the something much more realistic, much more interesting, compound interest, and we will use this formula over here, P1 plus RT equals the amount. Good. So compound interest. What is compound interest? Compound simply means interest on interest. So compound interest. This simply means when you earn interest on interest. What does this mean? Well, it's actually fairly simple. If you put money in the bank for a year and you receive interest after a month, and you don't touch that interest, you'll leave it in the bank. Comes the second month, you'll be earning interest not only on the principal you invested, but also on the amount of interest you received for the first month. So this is compounded interest. As you can see, it's actually pretty simple. So I will illustrate this. Trying to figure out the following problem. Suppose P dollars is invested at R% annual interest. The interest is always given annually. Compounded, so we need to know when is the interest given to you. So compounded, something pretty common, every month. So suppose P dollars is invested at R% compounded every month for 3 months. Let's leave the money in the bank for 3 months. How much do you have after 3 months? How much is in the account after 3 months? Okay, so we shall start looking at this from the perspective of that little formula that we had from simple interest, which was what? A is equal to P1 plus RT. All right, so we have this, and we ask ourselves, what is in the bank? First of all, what is in the bank after 1 month? Let's call that A1. Let's call what's in the bank after 1 month, let's call it A1. What do you have in the bank after 1 month? Well, you have your principal, yes, that you invested originally, plus you have your interest. Now, the interest is going to be, again, what we had before, which is what? P times R times T. So in that case, P plus R times P. So let's put a P here. And then the T, I'm going to say that T is 1/12. Why 1/12? Because it's the time. Remember the definition of time for simple interest? It's always calculated in terms of years. So if I leave the money in the bank for 1 month, I leave it in the bank for 1/12 of a year, right? So this is actually P1 plus R times 1/12, which I can write as 1 plus R over 12. That would be the amount that I get after 1 month. So there is no compounding so far. I just received interest for the first period, the first month. And then if I don't touch that interest, if I don't cash it in, I leave it in the bank, then the second month I will be receiving interest on that. So it's going to start being interesting really after the second month. So let's keep that in mind because that's what we have in the bank after 1 month. All right. So let's just like bring about what we have here. So after 1 month, we have A1 equals P1 plus R times 1/12, so R over 12. And let us ask, how much do I have in the bank after 2 months? what do I have in the bank after 2 months? Well, I will have something that I can call A2, no? The amount after like 2 periods, 2 months in that case. And this will be the amount that I had before plus the interest that it earns, plus the interest that will actually, let's call it interest for the first time you get interest, I1. And what is that? Well, what is that? This is A1 plus, how do we calculate interest? Principal times rate times time. Except that the principal here at the beginning of the second period is what you had at the end of the first times the interest times the time. So this is the old PRT, but P is A1 because this is what we have from the other period. This is the new principal if you want, and the rate and the time. So what is that? A1, well, A1 is here, isn't it? This is A1. This is A1 from here, from the first month, plus A1, again, A1, times what? R times 1 over 12. So R over 12, right? And now I have this plus this, so I can certainly take out what is common. And what is common between those two halves? Can you see? What is common between those two halves? P, 1 plus R over 12. That is what's common. Take it out from here, you get 1. Take it out from here, you get R over 12. And now 1 plus R over 12 times 1 plus R over 12 is P 1 plus R over 12 squared. So after 2 months, you get P times 1 plus R over 12 to the 2. Interesting, isn't it? You're starting to see a pattern because you're a clever bunch. So after, wrong color. After 1 period, we get this to the 1. After 2 periods, my red thing is really not working well, we have, it's really not working at all. We have a power of 2. So this is no coincidence that after 2 period, the power of the bracket is actually 2. Let's actually see what happens after 3 months. And then we'll be convinced that we have a formula at our fingertips for compound interest. So, okay, recall, this is our last line from the previous whiteboard. After 2 months, what did we have? We had A2 equal P1 plus R over 12 to the 2. So now I ask, remember that I put my money in the bank for 3 months, so this is the end now. This is going to be final. At the end of this 3 months, I close the account, I cash the money, I walk away. So A3 is actually going to be what? It's going to be A2, my previous amount from the previous period, plus the interest that they will pay me on A2. So what is this? This is A2 plus the interest on A2 is A2 times R times T. And again, this is for another month between month 2 and month 3. There's 1 full month, 1/12 of a year that goes on. So what's A2? Well, A2 is here. So P1 plus R over 12 to the 2 plus what is A2? Well, 1 plus R over 12. That's a bad R. That is a really bad R. To the 2 times this factor, R over 12. So once again, I have this plus this. There is something common that we call 1 plus R over 12 to the 2. What is left if I factor out this factor from here, 1? What gets from here is r over 12. That looks like an h. What's wrong with me? This is an r. And then, once again, 1 plus r over 12 to the 2 times 1 plus r over 12 to the 1 is 1 plus r over 12 to the 3. And that is a 3. So you can see here that a 3 gives a power of 3. So that is interesting. Let me actually show you one thing. 1 plus r over 12. I would like to write the 3 as follows. I would like to write the 3 as 12 times 1/4, where 12 is actually the number of months in 1 year, and 1/4 is basically 3 months, right? Because 3 months is 3/12 of a year. So this is the fraction of a year, in other words. So this is the fraction of a year, 3/12 of a year. You left the money in the bank for 1/4 of a year, 3 months out of 12, 1/4 of a year. And 12 would be the number of months in the whole year. It's also the number of times money is compounded in this problem, because money is compounded every month, which means money is compounded 12 times a month. And if we bring all this together, we have basically what we were looking for. We have a formula for compound interest that actually goes like this. So in general, we have that A is equal to P 1 plus R over N to the power of NT, where R is the, again, annual interest rate. Nothing changes here. T, time in years, even if it's a fraction, even if it's 3 months, 3 months is 3/12 of a year, 1/4 of a year. Time always in years. And the new guy, the new kid on the block, is this N here, and that's going to be like the 12 that I had before. In general, it's going to be the number of times money is compounded in one year. As for the P and the A, they are exactly as they were in simple interest. So P for the principal and A for the amount. About this guy, about N, if money is compounded yearly, then N is 1. If money is compounded monthly, then how many months in a year? 12. If money is compounded daily, how many days in a year? 365, and so on and so forth. There's obviously a lot of ways to compound your money within 1 year. Let me show you an example here in blue. So example, I'm not going to put it here. Put it here. Example, $1,000 is invested at 6% annual interest for 1 full year. Find the amount. Find, oh, I have a brush here. Find the amount if money is compounded. And here, let's play. Let's change the compounding period. Let it be compounded every month. Okay, so every month. So this is money given to you after every month. So after 1 month, interest. After the second month, interest, including interest on interest, and so on and so forth. So what do we have here, basically? We have that A is what we're looking for. We have a principal of 1,000. We have a rate of 6%. We have the time, 1 year, and the N, the number of times money is compounded in a year. This will vary. So in my case here, every month, this, I'm going to put it in a different color because it's going to change in the second part of the problem. Here, I'm compounding every month, so N is 12. So every month I have A is equal to P1 plus R over N to the NT. So that's 1,000. 1 plus 0.06006 divided by 12 to the power of 12 times 1. I put that into my calculator, and what I'm going to get is what I get at the end of a year when money is compounded monthly. I am going to get 1,061.68, I believe, dollars. Let's redo this. If money is compounded every day, so daily. What if money is compounded daily? Well, it's the same formula. Nothing changes except the N. What is N here? So monthly, N is 12. So here, daily, how many days in a year? 365. So my A is going to be P1 plus 0.06, or 12. And now to the power of NT, so 365 times 1. We put that into the calculator, and what we get is 1,061.83. So we get a little more money, not a lot, right? We get 15 cents more if money is compounded every day instead of every month. By the way, this is what your bank account gives you. Daily savings account is what it is called. Okay, suppose it is now, for the sake of the argument, compounded every hour. Ooh, compounded every hour. How many hours are there in a year? Well, there are 365 days and there are 24 hours a day. So 365 times 24, that is equal to 8740. So that the amount is again 1,001 plus 0.06 divided by N. So divide by a pretty big number, but the whole thing is raised to also a pretty big number, 8740 times 1. Okay, so actually it's 8760. I made a mistake here. My bad. 8760. I apologize. 8760, not 40. My bad. And if you do that, you are going to get 1,061.84. Hardly any difference, huh? Between every day and every hour. 1 cent more over a whole year. So that is really, really minimal. So that's interesting because it raises the point of what happens if I compound money not every hour, but every minute? Maybe not every minute, but every second. What if I do it every half second? What if I do it every millisecond? What if I do it like so fast that I can't actually even keep track of it? What if I compound money continuously? Aha. So this is actually the third type of interest that I want to cover with you guys in this video today, and it is continuous interest. So we saw simple interest, we saw compound interest. Now we're going to take a quick look at continuous interest. Okay. Now, continuous interest is an interesting concept per se, and it is the reason why we do what we do, because there's a little bit of calculus in the continuous interest perspective. So how do we start this? We have A is equal to P1 plus R over N. That's a really bad R. My R's are getting worse and worse, huh? R to the power of NT. So continuous interest would mean that I don't compound every day, I don't compound every hour, every minute, every second, every millisecond. I compound all the time. So the number of compounding times in a year would have to be really, really large, right? So how do I bring about calculus when I want a number to be really, really large? I take a limit as n goes to infinity. But that's exactly what we are going to do. What if n goes to infinity? What if n goes to infinity? So A, my amount, would be the limit as n goes to infinity of this 1 plus R over N to the power of NT. Let us call this equation 1. Let us call this equation 1, and we'll come back to it in 5 minutes. Okay, so I need to recall, before we can actually proceed any further, there was a very, very special limit that we saw last week. It was the definition of E. Who remembers what's the definition of E in terms of a limit? It's the limit as n goes to infinity of 1 plus 1 over n to the power of n that we saw last time, right? Remember we made a little table where we ended up with a 2.7181 value for E? I will simply say this. It can be shown, well, we're not going to show it, but it can be shown that if you raise e to the r, what's going to happen in this limit is that you're going to get here r over n. So yeah, it would have been more intelligent on my part to change the color here to really show what is going on. So e to the r, the only thing that it changes in my formula for e is a r on top of the 1 over n. Good. So I can actually now raise both sides to the power of t. So 1 plus r over n to the n. I would like to raise this as well to the power of t. So what I have here is e to the rt is equal to, okay, I'm going to multiply my exponents here like the rules of exponents allow me to. This is the limit as n goes to infinity of 1 plus r over n to the power of nt. Now I'm going to multiply both sides by p. So p e to the rt. And instead of having the p in front of the limit, I am going to use one of the rules of the limits to bring it inside. P 1 plus r over n to the nt. And I'm going to call this equation 2. And I'm going to call this equation 2. Now, obviously, how does math move forward? By combining different things. So equation 1 is here. Equation 2 is here. Please notice, I'm sure you already did because you're brilliant people, that this is the same as that. These two are exactly carbon copies of each other. So by combining them together, so 1 into 2, 1 into 2 will actually give me what I want. The formula for compound interest, A, is, that's a bad R. Again, I cannot do R. A, the amount, is P times E to the RT. This is the strange formula for continuously compounded interest. Continuously compounded interest. Very good. So we're coming to the end of this video. Let us do an example or two to basically show how this formula works. So example 1, on compound interest, find the amount when $1,000. Let's keep the same numbers as in the previous example. So to compare, compounded daily, compounded hourly, and now continuously, do we get a lot more because we compound every milli fraction of time. Find the amount when $1,000 is invested at 6% annual interest for 1 year if money is compounded continuously. So no more A is equal to P 1 plus R over N to the NT. Now this is the way to calculate continuous interest. So again, P is 1,000, R is 0.06, and the amount of time I leave it in the bank in terms of years is 1. Nothing could be simpler, right? So 1,000 e to the 0.06 times 1. Surprise! The answer to this is 1,061 and 84, which is, if I'm not mistaken, the same as the amount of money compounded daily that we calculated before. Ha! So that continuous thing doesn't really mean it's going to make you very much richer. Okay, one last one. How long will it take for money to, let's say, triple itself at 6% continuous interest? So the same compounding period as before, 6%, same rate, but continuously compounded. So go aside and try to figure out what needs to go into the formula. So R and T, what do we know? The only thing we know, basically we want the time, and the only thing we know is the rate, which is 0.06. We're not given what is invested originally, we're not given what is in the end, but we know that money triples itself. So here's what we could do. We could say, put in the bank $1,000 and it'll triple itself whenever you have what? Whenever you hit 3 times that, so $3,000. So we could go with that, and then we get into the formula PERT. We get 3,000 is equal to 1,000 e to the 0.06 t. You see, it doesn't actually matter what you put there because you're going to divide both sides by 1,000. You're going to get that 3 is e to the 0.06 t because you divided both sides by 1,000. And now you want the t that is in the exponent. So the best way to do that, you probably remember a little bit from high school, is to take the ln on both sides. So that the ln of 3 is, let me use that rule of ln that says if you have like a power, you can actually bring it in front of the ln. Remember that? We use that in logarithmic differentiation. So 06 ln of v. And ln of v, if you put that into the calculator, you're going to get uno. So ln of 3 is 0.06 times 1. And, oops, I forgot my t, sorry. 0.06 t. There it is, 0.06 t. I forgot my t, times 1, which is my ln of E. So t is what? ln of 3 over 0.06. And if you calculate that, you're going to get about 18.3 years. This is how long it'll take for money to triple itself under the condition of 6% continuous interest. All right, that was a longer than usual video. Hopefully you learned a thing or two. You can join me for the next video where we'll actually take a look at some more financial and economic applications of calculus, this time with more derivatives and also a few limits. In the meantime, take care. Have a great